Thank you for joining us for our discussion on Persyst 14 and quantitative EEG for continuous monitoring. My name is Michael Guess, and I am the VP of Research and Clinical Applications for Persyst. Today, we will be exploring quantitative EEG and detection technologies for EEG in the EMU and the ICU. And here's what we'll be talking about today. We'll discuss the utility of trending for online monitoring in addition to review, and we'll look at a couple of techniques to improve recording quality with digital EEG systems, regardless of the one that you're using, since EEG quality is still fundamental to all of this. We'll take a brief look at the effect of trend duration with a couple of clinical examples, and then we're going to go through a technical overview of a variety of trend types and their functions in detail. What is the trend showing? What happens when I adjust it? What happens when I zoom in and out time-wise? Now in part 2, we'll look at sets of trends working together, what we call trend panels. We'll look at the utility of statistical change trending and how we can now track changes over time across hours or even days of recording. And we'll do a brief overview of the analysis of periodic discharges and spikes, looking at the use of trending and spike classification to look at these types of events in a more quantitative way, from the street view to the satellite view, if you like. And we'll finish up part 2 looking at the use of mobile technologies within the hospital for monitoring and review by technicians and physicians. And we'll also look at how those technologies can be applied to monitoring of notifications and review from outside the hospital in a way that is robust and secure. Okay, so let's start with recording quality because that's fundamental to everything that follows. Now, in some facilities, square wave calibration and biocal is still commonly done, and this is a practice that has been done for many decades. So what's behind it? Well, square wave calibration was used back in the day of analog systems to adjust galvanometer gain and the downward force of the mechanical pens against the paper. Because the pen drag on the paper acted as a low frequency, the harder the pens pressed against the paper, the longer they would take to go back to baseline. And so you used a square wave cal to help adjust the force of each individual pen against the paper. Now in digital EEG amplifiers, the square wave is a synthetic signal that never passes through the amplifier, and so it doesn't really calibrate anything. There's nothing mechanical to calibrate. Biocalibration was then done on pen and ink systems to feed a dynamic signal with lots of different frequencies into each channel. And that was typically FP1 to O2, so that you had a large signal, and you could see if each one of those mechanical pens and galvanometers were responding the same to a dynamic signal. So what happens in digital EEG is something similar to that. Since everything is recorded referentially, you take FP1 to the reference, O2 to the reference, subtract that reference, and then copy-paste down the page. Now, these were required of digital EEG systems, and they still commonly are. But is there something that we can do that will be more helpful? Because if we follow the common practice of going from square wave cal to a biocal, FP102 biocal, to a bipolar montage, we still haven't seen the one electrode that's common to all the inputs, and that's the reference, the amplifier reference. So there's something called a digital biocal, where you can record each amplifier input, each EEG scalp input, to the amplifier reference. You have the filters set fairly unrestricted, notch filter off, and now the technician can see the one channel that's common to everything and arguably the most important channel in the recording. And if there's any problems with a contaminated reference or a bad reference, it can be seen and resolved pretty easily and quickly in most cases. And so even if you do a square wave calibration and a biocalibration, if that's followed up with a bit of digital biocal, all those inputs to the amplifier reference with the notch filter off, then they can see what's happening with each individual channel, have a look at the amplifier reference, correct it, and this practice can have an immediate effect on recording quality because the technician can see that one common electrode to all of them, resolving issues, and then the recording goes on as usual. Of course, analog systems are exceedingly rare, and with the introduction of digital, one of the greatest things was you could change montages at any point in the recording during review. You could apply filters based on the artifact in the recording, and filters, while they're used for some other purposes, are generally used for scalp EEG to reduce the influence of artifact. If we have a lot of muscle artifact, for instance, we can apply a low-pass filter or a high-frequency filter, take it down about 15 hertz perhaps, and help reduce the contribution of that muscle artifact. The problem, of course, is that a filter doesn't distinguish between cerebral signal and artifact. And so after several decades of digital EEG and all the advantages of that, Persyst introduced automatic physiological artifact reduction. And what that does is it uses a number of techniques to spatially separate cerebral signal from physiological artifact and represent both. So you can see in the second image there, the right-hand one, where we have a trend of electrode signal quality. So in addition to physiological artifact reduction, it's also looking for bad electrodes and subtracting those from detection and trending, so we don't have those contaminating the results of those. And we'll look at the effect of that as we go forward. But here you can see the original signal is in the shaded color on the right, and the artifact reduced signal is in black. And the idea with artifact reduction is that you get a much better signal to noise ratio than if you were to use a low pass filter to help reduce muscle artifact. And so this helps preserve the morphology of the waveforms and does what you actually want it to do, which is to help reduce the artifact so you can see the cerebral signal. Now that helps with seizure detection, spike detection, and trending, and we'll look at the effects of those as we go further into this webinar. And so our talk about quantitative EEG in the ICU and the EMU will include these technologies, the artifact reduction, the automatic identification of electrode artifact, and so forth, because they're available today, and they are fundamental to reducing barriers to adoption that were the rule for the last 2 decades. Now, before we go into the details of various detection technologies and trends and how they work, let's have a look at some of the issues that we're trying to help with, some of the problems we're trying to solve, and some of the ways that we can maybe get a better view of what's happening with the patients. Just to step back and look at the amount of data we're dealing with, we have 8,640 10-second pages of EEG per patient per day. And if that was run on paper, it would run for nearly 1 kilometer for each patient. So data reduction is one of the issues that we want to have a look at. Also, ICU continuous EEG recordings are very long and they require frequent assessments. And in addition to that, we have these slowly evolving changes that are difficult to recognize with the intermittent page-by-page review, and changes in brain function can occur frequently and unexpectedly. So this is a monitored room, and it is apparent that it would be difficult to see something that has already scrolled off the screen. It is also difficult to see slowly evolving changes that may span hours and multiple recording stages. So what can we do to help make this work a little bit better? So let's take a closer look at what we're trying to see. Let's start with what we get to see when we're monitoring a patient. Now this is a widescreen, so we get a little bit more EEG data. This is about 21 seconds of EEG. And the obvious question is, how do you know if a clinically important event has happened if the monitor is viewed after that event has scrolled off the screen? We've got 21 seconds of history. Now, one thing we can do is add more pages. And actually, there's a mode in Persyst, in Insight 2, where you can put lots of pages of EEG up on a single screen. So here we have a screen showing about 160 seconds of EEG, and it's in 3 rows from left to right. So we get a little improvement here. As soon as we step back a bit, though, it gets a bit hard to see the finer details. So it's one thing we could do, but again, we're heading in the right direction. Now, review is a different situation where we want to do data reduction. We want to be able to find those clinically important changes, help increase our yield of recognized seizures. When you're monitoring, you don't want to miss stuff, to put it in a nutshell. And so how do we have our current display of what's happening with the EEG? We want to see what's happening in the video at present, but we also want a rear view mirror that doesn't crowd out what we're trying to see. We want to see what's scrolled off the screen. We want to have an idea of what's changing over a longer period of time, because in the ICU, again, you can have these slowly evolving changes or other state changes in the EMU that we're interested in seeing. And frankly, we may have taken our eyes off a monitor to look at another one, and if it's already scrolled off the page, what do we do? So here's something that you can use to provide a live, longer duration view of multiple patients as they're being monitored and all on a single display. So this is not replacing the live streaming EEG and video. You can think of this as a rear view monitor for each patient. So here's a display of 6 different patients, and in each we can see seizure detections. And so without digging too far into what each trend will do, we're going to do that in a moment. At this top middle one, I can see these red marks for seizure detections. Not hard to pick that out. We can also see this change in the rhythmicity spectrogram. This curved pattern indicates something that's rhythmic and evolving, which is one of those hallmarks of a seizure. We see changes in the other trends as well. Go to the upper right. Again, we can see these seizure detections, these change in patterns pretty easily. Bottom left, we have some state changes. Bottom middle here, we have 2 seizure detections, and we see these patterns here, these patterns with a shape indicating evolution of a rhythmic pattern in the EEG. And so all of these gives us some information about what's happening with each one of these patients, but not just over the last 10 or 20 seconds, but over the last 30 minutes or so, based on the monitoring environment. Typically for the EMU or an ICU, you're going to show 30 minutes to an hour for each patient. That's considerably more than the 10 to 20 seconds of history that we're usually limited to. Now let's take a quick look at trend durations. It'll give us some context for what we're going to look at with respect to the individual trends and what they're showing. We're going to look at changing the gain of the trends and the duration of those trends and see what effect it has in our ability to see changes in the underlying EEG. Here's a 24-hour trend duration on the right, and in these very thin slivers at the top of the trend panel, that's in the seizure probability and seizure detection rows up at the top, we can see those detections, but the seizures are minutes in duration. And so they're too short to show up. When we scrunch 24 hours of trend data on that, we can see these slowly evolving changes. We can see the waxing and waning of spike detections around each one of these seizures, but the patterns associated with them we can't see. So let's see what happens when we zoom out. Or zoom in, I should say. Let's zoom into 1 hour. And so for seizure hunting, 30 minutes to 2 hours is pretty typical. And the reason for that is we don't want to rely just on the detections. It's nice to have those. They help us indicate where we want to focus our review, but there's more information here, and we can help increase our yield of recognized seizures if we have something to go along with that. For instance, we have an increase in spike detections leading up to the seizure that we can see in the trend below the seizure probability. And in the rhythmicity spectrogram, we can see that pattern that's typical of this particular seizure morphology. We've got something going faster to slower, starting at the upper part of that trend display and angling downward. That means we have a pattern that's rhythmic or periodic that's going faster to slower. It's evolving. And so by having both the detections and the trend panel duration set to where we can see those patterns in the trends, that helps increase our yield of recognized seizures. Now here's an example of a slowly evolving change. We're looking at 1 hour trend duration, and as we look from top to bottom through these trends, the immediate thing to notice is that there's not a lot of change when we're looking at the left end of this trend display over to the right. It's pretty stable. So what's happening? Let's zoom out and see if we can see more of the picture. Now we've changed the trend duration to 24 hours, and there's steps between this. It's not just 1 or 24 hour. You can step it up to 4 hours or 8 hours and so forth. So we've zoomed out to 24 to illustrate that sometimes things evolve slowly. And zooming out in that trend, you can see that. And where we see it most prominently here is in this asymmetry relative spectrogram, where blue is increasingly left-weighted, red is increasingly right-weighted. We have an increasing left-weighted asymmetry rolling through this from left to right. And that shows up most prominently in the AEEG display, where we're showing left hemisphere in blue, right hemisphere in red. Pink is overlap, and so we have higher amplitude on the left, and as that right hemisphere EEG drops in amplitude, that overlap decreases, and we see that blue increasing across, and we see the red increasing along the bottom edge of that. So this is an example where zooming out can be helpful. And so there's no one right trend duration. If you're seizure hunting, 30 minutes to an hour is good. You can see shorter duration changes with a trend panel of that length. If you're looking for slowly evolving changes, you can stretch it out a bit, click that zoom button up at the top, change the time domain, and zoom out and have a look. But it's important not to get stuck in one time duration or another. It's just like zooming into the street view or zooming out to a satellite view. There's not a right view. It's the idea of picking the trend duration that lets you see what you're hunting for. So let's go ahead and from there move on to looking at individual trends. Okay, so now we're going to go through the different trend types that we're going to be exploring in detail. We're going to start off with detector or event density trends. That's just a trend that shows when something is indicating true for whatever that detector is looking for. Then we're going to go into amplitude trends. Those are going to rise up and down based on the amplitude of the EEG, just like the EEG waveforms go up and down based on the amplitude of the EEG signal. Then we're going to go into power ratio trends. That's where we're going to take something and convert that amplitude at whatever frequency into a trend that moves up and down based on the amplitude of the EEG at a particular range of frequencies, or we can take those and turn those into ratios. Next, we're going to look at three-dimensional trends. So that's where we're going to change looking at things that are in 2 dimensions to 3 dimensions. What does that mean? It just means that left to right is time. And instead of up and down indicating a change in amplitude, the vertical axis is going to be frequency, and we're going to use color change to indicate a change in amplitude. So we'll go over that in sufficient detail. And one of those spectrograms that is different from an FFT spectrogram, of course, is a rhythmicity spectrogram. We'll demystify that, and then we're going to look at artifact intensity and signal quality to wrap it up. So, detection and event density. So, event density can actually be generated to give an indication when a comet has been placed or a duration comet has been placed. But it can also be generated from detectors placing comets. In this case, we're going to talk about the output of the seizure detector. Spikes and sharp waves, you can show those as comets, but we can also trend those so you can see when they're happening and how often they're happening, at what rate they're happening. Same thing with heart rate. Those are detecting QRSs, and if we calculate the number of those per minute, we get a heart rate. Here the event density trend for seizure detections is displayed along the top, actually the second most trend in this trend panel. And if we zoom in on this to highlight the output, we have comets, seizure detected, showing up. We don't really get a sense of how they're happening in time, but with the trend, we're looking at a 30-minute trend versus baseline comprehensive. We have seizure detections and probability. When the probability goes above a certain level for a certain amount of time, then we have a seizure detection output, and that's what we're showing here. It's either there or it's not, and we can see in this 30-minute we have 3 seizure detections, pretty evenly spaced. Let's look at another way of trending events, in this case spike detector events, and there can be many more spike detections in a recording. Now, a list of automated spike detections is not necessarily the most useful, informative, or efficient way to look at spikes because it doesn't do a great job of answering those preliminary questions. I suppose the first one, are there spikes and sharp waves? You can click on those and go to the individual detection. It doesn't really answer well the question of when they're happening, where they're happening, and at what rate they're happening. But this is the way that spike detections were represented at the dawn of automated detection back in the 80s. So let's look at a page of trends showing these event densities, and we've zoomed in a couple of portions here. We're looking at a 2-hour duration for this particular example, and we're zoomed in on the spike detections, all foci, count per second 0 to 3, and count per, if we have greater than 3 per 10 seconds on a page, basically more than 3 per page. So the 0 to 3, what that means is that if it's a third of the way up, it's 1 for each one of these black marks. If it's 2/3 of the way up, there's 2 of them per second, all the way up 3 per second or greater. Below that, these are color coded, so if it's greater than 3 per 10 seconds on the left, it's blue, right is red, yellow is left and right, and green is generalized discharges. So it tells us a little bit more about how often they're happening, but also where. Now on the left part of this trend, it's pretty sparse, so we don't expect to see a lot of detection showing up when we click at the left part of this. So let's see what happens if we go a little bit further and we click where this density of spike detections is much greater, and this really becomes pretty solid. as expected, we see a lot more detections here. So this gives us a way to find areas of the recording where spike density or spike rates are low, or where they may be higher. And again, that information about lateralization. Here we have LPDs, and the spike detections pretty solid throughout. On the lower trend, we're seeing that there's greater than 3 per 10-second page. That's true. And this is pretty solid blue, indicating that these are left hemisphere detections. So let's look at spike bursts. This is a short run of generalized spike discharges, and as expected, that's rendered in green. So we have the spike detections, all foci goes all the way up, indicating that it's 3 per second or greater. And these are classified as being generalized detections in the trend. So this is another example. This is an ESIS patient. The EEG page that we have displayed is at a point where the spikes are present but not continuous, and the spike rate trends become solid when the EEG becomes continuous spike wave. And so if we click over to this part of the trend, we were over on the left part before. Again, this is just zoomed in so we can see it a little better. This becomes pretty solid over here, and we can see the spikes have become continuous. Now we can use this information to calculate the spike wave index, and that's traditionally been done by hand, where you go to a page and you say, is that epoch true for spike wave or not? You go to the next page, you make the same assessment, and you determine the percentage of epochs that were true for spike wave or not. And that can be a tedious process, time consuming. So is there a way that we can be perhaps more consistent with this, or do this in a more efficient way? When we use the spike detector to help us with this. So we have this spike rate shown in the spike trend. And what we do is we just place a comment with the duration, and then we go to Tools, Spike Index Tool. And if we've marked it with whatever comment we want, in this case we've used an @ symbol at the front, so it's at the top of an alphabetized list of events. It makes it easy to find if we're looking for it. And we've marked a range, and we've told it to calculate the spike wave index using a 1-second epoch duration, and let us know if there are more than one spike per second, and if so, we're going to count that 1-second epoch as true for spike wave index. And here we have the calculation. We've marked 2 ranges in this particular recording. It tells us the duration of those, the number of spikes that were detected, and it gives us a spike wave index of 70.2%. All right, this is the last event density sort of trend before we go into amplitude-based trends. And the event density here, or, well, the event density of QRS detection. So we have a heart rate trend, and this is looking for the QRS, and we've set this to look at the channel's ECG to reference. In current versions of Persyst, you can actually have different derivations identified in case you use a different designation in 2 different places of the facility. It can support that. So, but the basics, we give it the channels, and by default, we're going to average the number of beats, and they average the last 15, step it 1 second per epoch, and the output of that is heart rate. This is an algorithm that's been optimized for use in the EEG environment. So that's a place where we can expect a fair amount of artifact, but ideally we want to have as clean of EKG signal or ECG signal as we can get. But it is, again, optimized for this sort of recording environment. And if we look at how the trend works out, here's an area of lower heart rate, an area of higher heart rate that we've highlighted, and we can see that change here. Now, in some cases, you may end up with an EEG where the seizures may not have a very distinct cerebral signal, but it has a significant signal in the heart rate trend. So anything that can help us increase that yield of recognized seizures, once we found something that's a good indicator for that, we can continue through the record, perhaps in a more efficient way, and increase that yield of recognized seizures. Moving to our next category of trends, these are based on amplitude, and that includes the amplitude integrated EEG, also called AEEG, suppression ratio, which is actually an amplitude trend, and peak envelope. Let's start with amplitude integrated EEG. Important thing to know about AEEG is that it is both linear and log. And what we've done here is this is a synthetic signal. We've labeled it F4 to reference, but it's just synthetic. We have a sine wave. First one is 10 microvolts, then it goes to 50, and then it goes to 100. Now, how's that represented in an AEG? We don't normally see AEG represented second by second as we do here, so it's a good way to see what it's doing. So at 10 microvolts, as we'd expect, it goes to the 10 microvolt line. So the first lower part of this is 0 to 10, linear. But then when we go to 50 and 100 microvolts, we're no longer linear. It goes to 25, 50, and 100. So this is the high amplitude part of this, and the bottom part is the low amplitude. Why did we do that? Well, when Maynard did this back in the using his asymmetric filter back in the 60s and 70s, the semi-log scale was what was designed to help resolve low amplitude in EEG. This is this bottom half, at the same time be able to represent high amplitude EEG and to still resolve those changes in amplitude. So it stuck around and stood the test of time. That's what the amplitude integrated EEG is doing. So let's look at it in a clinical setting, and we're going to compress the time. So now we're looking at 30 minutes, and we've zoomed this AEG trend display, make it a little easier to see. This is not something you do in the software. This is something I did to make it easier to check out as part of this webinar. So we're doing it a little differently here. We're still representing it in the traditional way using the Maynard asymmetric filters, 2 to 20 hertz, but we want to not only see changes in amplitude, but we want to see changes in symmetry and help save a little space on the trends, because things can get a little crowded if we don't find some ways to save some room. So this benefits all three of those purposes. We're showing left hemisphere in blue, right hemisphere in red, and amplitude symmetry in pink. We don't see a lot of symmetry here. But what this does tell us is that the amplitude on the left is higher than the amplitude on the right, except during the seizures. The amplitude on the right goes higher. The left stays pretty steady throughout. So what we see is that the amplitude on the right goes higher during these seizures. We can see the seizure detections up at the top. We see this seizure pattern in the rhythmicity spectrogram that we'll be getting to later. But again, that amplitude on the left, fairly steady throughout. It's the amplitude on the right goes up during the seizure, and then it falls during the interictal period, and then goes back up again for the next seizure. And so always going to the EEG page to see this in context. And since the text may be a little bit small for the channel labels, what we're looking at is channels on the left, and then right, and then left, and then right in groups of 4. So EEG on the right is lower in amplitude than the EEG on the left. Let's go to where that changes in the trend. So now we're looking at this part of the trend where that amplitude has increased, and we can see that the amplitude on the right has increased as well. All right, moving on to the suppression ratio trend. Here's the suppression ratio. We're showing this in the middle. So at the top we have AEG left hemisphere and right hemisphere. We're not showing them overlapped. We're at a 6-hour trend duration. And below that we have suppression ratio. This is showing left hemisphere in blue, right hemisphere in red. And one of the things you notice is you look over to the right, because we're going to talk about this in the context of both the AEG and the artifact reduction. It looks like the right suppression ratio has fallen to 0 at this point, while the left is decreasing. It's still above 0 at that point. So what's happening? And let's also talk about what the suppression ratio is actually showing. So the suppression ratio doesn't detect suppression, and it doesn't detect bursts. What it does, by definition, is it takes 1 minute running average of EEG and calculates the percentage that is below 3 microvolts. So how much of that last minute as a percentage is below 3 microvolts, and then that increments a second at a time. And we get this waveform here. And so the higher that it is, the more time that EEG over a running 1 minute average is spent below 3 microvolts. And let's zoom in on the AEG. During a suppression burst, we expect the AEG to become very thick, and the reason for that is that at the bottom of this amplitude trend, the amplitude is very low, and as you go up, the amplitude becomes much higher. So AEG, when it's showing a thick banded appearance like this, or a thick appearance like this, it's indicating that the amplitude is alternating from very low to very high to very low to very high, on and on. So what we see in the trend for the amplitude integrated EEG, which has a shorter epoch length than the suppression ratio. Again, the suppression ratio, well, it's averaging 1 minute. This is moving second to second. So the AEG for the right hemisphere thins out as opposed to the left, saying that, well, it appears as though the EEG in the right is becoming more continuous. Let's find out a little bit more about what's happening. So we've jumped to this part of the trend. The cursor is over here, where that right suppression ratio has gone to 0. The right hemisphere AEG is thinned out, and we see that there's a muscle artifact that's showing up across the channels on the right. And that's affecting the calculation of the suppression ratio because, again, it can't drop below that 3 microvolt threshold when there's muscle present. So what do? If we turn on the artifact reduction for the trends, and this is independent, you have an AR button above the trends that you will normally leave on, and you have an AR button above the EEG, which can be on or off. Normally you leave it off and you turn it on when you want to separate that in the waveforms. So we've done it on both sides here so we can see the effect. And, well, one effect is that the AEG for the left and right hemisphere, this trend, well, looks pretty symmetric. And we see the same for the suppression ratio, where we don't have the left going to, we don't have the right rather going to 0 because these channels have muscle artifact. We've separated that so that these are now correctly representing the cerebral signal. Now here we're showing a peak envelope trend. It is a trend that's been around for a couple of decades. It's a very simple trend. It goes up when amplitude is higher, goes down when amplitude is lower, and it has some similarity with AEG in that it's looking at 2 to 20 hertz traditionally. You can change the range of frequencies. AEG is fixed function. Peak envelope can have different frequency ranges, but it is using an epoch length of 10 seconds. And so what this trend shows is what is the amplitude between 2 and 20 hertz for each 10-second page. And you can see that it's going up during this spike and wave seizure, and then it goes back down at the end of that seizure. It doesn't give us a lot of information. It's really just an amplitude trend with some information stripped out. So the AEEG trend has higher time resolution, whereas peak envelope, again, is saying what's the maximum amplitude between 2 and 20 hertz for each 10 seconds. It has the advantage of simplicity, but it has the disadvantage of blurring out a lot of other details. So you don't see it used quite as often these days, but it is still available. Now let's move on to frequency-based trends. We did look at some amplitude trends that were bounded by frequency, AEG 2 to 20 hertz, using a asymmetric filter, which just means it's not this flat filter. It attenuates more frequencies versus others within that 2 to 20 hertz range. And there's details of that in the user guide, and of course you can always meet by a web conference, but we're going to talk about something different in this case, which this is a term you come across all the time. What's a FFT? We'll answer that question. And we'll show how that's used for band power trends. We're going to show amplitude by frequency range, delta, theta, alpha, beta, for instance, or whatever ranges you want to use, and ratio trends, those that include the traditional alpha-delta ratios, relative alpha variability, and we'll go through the details of that. So starting off, we should find out, well, what is this FFT? What is it doing? And this will be a very brief overview. There's some really fantastic stuff on YouTube that goes into the details of how the most famous algorithm in the world, the fast Fourier transform, has an interesting history. And it has a reason for why it's called the fast Fourier transform as opposed to the Fourier transform. And we won't dig into the details of that. Let's just see what it's doing. So if we go to the original EEG, F4 to reference, there's the signal. And we're going to skip over the reconstructed part. We're going to look at what the FFT does. It breaks down the signal into sine waves by frequency. And so we can see here we're going successively from lower to higher, or different frequencies within this pattern. And we can measure the amplitude of those sine waves to determine what the amplitude by frequency is. And that's done by frequency bin. So in Persyst, the default frequency bin size is 0.5 hertz. That is adjustable, of course. there's a trade-off between time resolution and frequency resolution. So you find something that's appropriate to the application, which we believe we've done in that configuration. And then you can add those up to get band power. So if you have half hertz bins, you can say, all right, I want to do delta, theta, alpha, beta just by adding the bins together that make up that frequency range, and you get an amplitude. Now the other thing, of course, is you can take these sine waves and you can put them back together and reconstruct the original signal. And the fidelity with which that's done really depends on the FFT parameters. That's not something that you do clinically, but it's just something to know that those sine waves actually can be recombined to recreate the original signal. So one of the things you can do with FFT power is you can, again, add those bins up to create delta, theta, alpha, beta ranges. And here we're doing that looking at left hemisphere and then right hemisphere. So the blue is delta, then we go to yellow for theta, green for alpha, and then blue, light blue for beta. And here we are at the onset of a seizure. And since at the onset here we have higher frequencies on the right, we can see the right hemisphere, 13 to 20 hertz beta is increasing. Now this is averaged over 2 minutes. It's a 2-minute running average. That's a traditional way of showing band power, as well as other ratio trends. Specifically alpha to delta ratio, you tend to time average those to smooth it a bit. And so that's what's being done here. So that's not required. You can show them at the full resolution of the FFT, but averaging them obviously smooths things out, makes it a little easier to see slowly evolving changes. Artifact rejection helps with this as well. So we're automatically identifying bad channels, which we don't have here, physiological artifact. And so we're representing the cerebral signal better than we could before the days of artifact reduction. So one thing to note here is this starts out at faster frequencies. If we look up towards the delta at the top, that one hasn't really started to deflect yet. Let's move a little further into this. So we'll go to the offset. Here we can see the EEG is much slower. And we can see that we're getting towards the end of this deflection here. Again, it's averaged over 2 minutes, so it's still up there, but it'll begin to fall pretty rapidly with the offset in that seizure. And the theta and delta graphs are picking up at this point. So you can see that there's something that's changing over time where we do have an evolving pattern where we have higher power in the faster frequencies that gradually moves slower. But you can see with the resolution and the separation of frequencies using band power, we're going to assemble those into a spectrogram and get a little better view of what's happening with respect to this evolving rhythmic pattern. Moving on to alpha delta ratio. This is by hemisphere and by quadrant, which is one traditional way of doing it. We can also do it using anatomical regions, identifying those by channel labels as well. So that's going to be, and Persyst 15 is a default setup because that's a bit of interest. Probably not a great deal of difference between what you're going to see in one versus the other, as opposed to just making it a little bit easier to interpret those as you're moving along through a record. So let's look at what we have here. We have ADR, 2-minute running average. Again, that's tradition is to time average these. We're showing the right hemisphere in red, left hemisphere in blue. And this is 8 to 13 hertz over 1 to 4 hertz. This is left and right hemisphere. Then we look at this by quadrant. So we're looking at left anterior in blue, right anterior in red below that. And then we have left and right posterior, same color setup. Now below this, we're showing some information about symmetry and amplitude, because we like to include amplitude trends whenever we have a ratio trend. And by the way, an asymmetry is a ratio. We're looking at the relative amplitude of homologous electrodes between left and right hemispheres by frequency. We'll get into that later. But everything above this amplitude trend is really a form of ratio trend, explicitly or not. But what we're looking at is the loss of faster frequencies as this trend goes downward. Now the denominator is 1 to 4 hertz. So these can actually go quite high. If you're looking at a period of alpha, you can get very high ratios. But the typical scaling is 0 to 2 for the ratio. And here we are. We can see that this is a carotid endarterectomy, actually. You can see that there's a significant asymmetry between left and right. The right didn't increase in amplitude. So this is, again, we see this drop here in ratio on the left. And we see the asymmetry spectrogram showing that the right became more prominent, but it wasn't that the right increased in amplitude. How can we tell that? If we look at the AEEG trend, it's pretty easy to see that we have amplitude symmetry running along until that clamp, and then we can see the left amplitude dropping pretty dramatically, and that made the right become much more prominent. And that asymmetry is in the faster frequencies because this is sitting up towards the upper part of this range, 0 to 20 hertz. But looking at ratios, again, that ratio, as we lose faster frequencies, we expect this to decrease. And that's an example of that. Let's look at the same section of EEG using relative alpha variability. Now the difference is there are two differences. One is that the ratio is 1 to 20 hertz instead of 1 to 4 hertz as an alpha delta ratio. So it is 8 to 13 hertz with 1 to 20 hertz as the denominator, so it's not going to go above 1, which is why the typical scaling is 0 to 1. It's also not time averaged because you're looking for variability as the recommended way to use a relative alpha variability trend. So it's a visual estimation of variability. And as with the other ones, we like to include an amplitude trend. So in this alpha variability, we can see the loss of faster frequencies over the left. And here we have left anterior, right anterior, left posterior, right posterior. So there's that loss of faster frequencies at the clamp. And we can see that we indeed lost amplitude on the left, whereas the amplitude on the right stays fairly steady looking at the AEEG. Okay, continuing on to frequency trends using the fast Fourier transform, we're going to look at a difference where up until now we've been looking at two-dimensional trends where that vertical axis is either a ratio or the amplitude at that frequency within that frequency range. Now we're going to add a third dimension. So left or right is going to be time. That's not going to change. Up and down is going to be frequency. The vertical axis is going to be frequency, and the change in color is going to indicate the change in amplitude at those frequencies, and we call those spectrograms. We're going to talk about units and scaling and time scales, what the effect of changing those is. But let's see what we're looking at when we're looking at a three-dimensional trend. And this is going to be going back into the old days a bit, what they called a hidden line CSA. And this is laying it out in a pseudo three-dimensional way. We're looking at T3, T5 on the left, T4, T6 on the right. And the higher the amplitude at the frequency being plotted, you'll see a line go up in that pseudo 3D dimension. So the bottom scale is frequency, so we're going 0 to 30 hertz. And as we look at that vertical axis, this is going back in time. So you can think of these being added and then kind of receding to the background. And this was the way that it was done some decades ago before computers could do high color and high resolution at the same time. But you can see here that there's power or amplitude at frequencies, and that's changing over time. So what we have is an evolving evolving pattern here. We don't know if it's rhythmic or not looking at this. And it's fairly stable on the left channel T3, T5. So this is the way that FFT spectrograms were rendered back in the day. So let's move to today and look at that same recording, but showing these in a color scale. And so here we're using a color scale that has been traditionally used on some systems. So Persyst can use different color scales. And here we're looking at left hemisphere, all those channels averaged together, 0 to 20 hertz, and right hemisphere. And the scaling, if you look over on the right, bottom is 0 hertz, top is 20. So this is the frequency scale, not the amplitude scale. And this increasing brightness in color, this is increasing amplitude at that frequency. So if I look at where the cursor is sitting in the middle of this trend that's situated above the EEG, we can see this rhythmic pattern that's beginning to show up on the right. And if we were to page through that, we'd see that going from faster to slower. So there's that sheet music analogy where the high notes are up at the top, low notes are towards the bottom. And as we page through this, I would expect that this will evolve from faster to slower on the right hemisphere because it's going downward Again, the color is the amplitude of the EEG. Its position on this vertical scale is the frequency. So this is using an RGB, or red, green, blue color scale. This is the one that's used more commonly in Persyst. And again, this is more about tradition and the way things have been rendered over time. There's not a right or wrong. There's different color palettes that may be more suitable. If somebody has color blindness, for instance, you may not want to use this sort of trend panel. You may want to use one with a different color scale. So all that's adjustable. There's that same pattern. They've been traditionally referred to as flames. There's that decreasing frequency as a seizure evolves. So let's look at the effect of scaling using a different recorder. Now we're going to look at a carotid endarterectomy. And what we have here is left hemisphere, right hemisphere, displayed above the EEG. And where the cursor is positioned, that's where we're looking at the waveforms in relation to this position on the trend. So we see left hemisphere where it's becoming a bit darker. We're losing the brightness of the colors here. And what that's telling us is that in the EEG, we're losing amplitude at those faster frequencies in comparison to the right hemisphere. And we've scaled this at 2 microvolts per hertz. So the reason that it's microvolts is, well, we're using microvolts as our units of amplitude. Per hertz just means is where is it in this vertical scale? So that's the per hertz part. And we're taking the square root of those. So you can see the SQRT scaling. And the reason for doing that, as opposed to using the raw microvolt values, is that you tend to have much more amplitude in lower frequencies than you do in the higher frequencies. And what can happen is if you scale things so that you can see these changes at the faster frequencies at the top easily, the lower frequencies may just be blooming off scale. And ideally, you want to be able to see changes at the faster frequencies and the slower frequencies without having to adjust the scaling too much. Now there is a scale there. You can click on that color bar in the upper right and you can adjust the z-axis scaling, that color range, to get the best view. So if you have EEG that's unusually high or low in amplitude, by all means adjust that just like you'd adjust the gain in the EEG. But here we can see some pretty good resolution, and we can see that loss of faster frequencies on the left. Now if we change this, just to have a look, we increase this to 3, we can see that this has gotten darker. We're at the lower part of the scale. Now we're going from 0 to 3 microvolts, the square root values of each microvolt value, and we don't see as much blooming at the bottom. We can see that loss of faster frequency still. So this, changing it from 2 to 3 works fine. You might be able to see those changes at the faster frequencies a little easier with this. And let's see if we go even further, if we go up to 6. Well, now we've gone too far because now we're just using the very bottom part of this color scale. Nothing reaches up into the greens or the yellows or the reds. And so we're getting less dynamic range, as it were. And it makes it much more difficult to see changes in the underlying EEG. So this is when you scale it too high. Now here's another look at an axis. So we've looked at scaling the microvolts per hertz. Let's look at change in the time axis here. And so now this is set to 1 hour. And this is a recording with 3 hertz spike and wave seizures, and they're about 14 seconds long. Now, FFT spectrograms show all the amplitudes, not just the rhythmic components. We'll look at rhythmicity spectrograms in the next section. And so the seizure patterns are visible, but not as distinguishable from other non-rhythmic activity. So we don't get that distinction. But let's go ahead and see what happens if we increase the time range here to 4 hours across the top. That seizure just becomes very thin line in this spectrogram, very difficult to pick those out. So this is an example where you have short duration seizures, and we've increased that time range to 4 hours over that trend, and it just becomes too difficult to pick those things out. So that's what happens if we pick a time duration that's a bit too long for what we're hunting for. Now, one thing we can do is we can average channels together. Back in the day, it was not uncommon to do a trend per channel, because if a channel went bad, you could just visually ignore it and say, well, I'm not going to look at that particular trend. But with artifact reduction, reducing the contribution of physiological artifact and identifying most types of electrode artifact and subtracting that from the trend, it gives us a chance to save some space. So we're using left and right hemisphere. So we have left hemisphere and right hemisphere for rhythmicity spectrograms that we're going to look at, left and right hemisphere for the FFT spectrograms that we just explored, rhythmicity spectrograms rather. We have the asymmetry spectrogram here, hemispheric, 0 to 18 hertz, looking at differences between left and right hemispheres. We have the AEEG trends that we covered earlier. By using hemispheres, we can put more types of trends on a single panel and help us look for different features in the underlying EEG. Now, having said that, we can combine channels into groups of channels like left and right hemisphere or by quadrant to help make a more compact display with different types of trends to look at the EEG in different ways. Here we're looking at rhythmicity by channel. We're going to look at those, what creates this or how this works. But here we're doing individual channels. And we can see that the seizure of which channels that seizure activity is more prominent, pretty clearly looking at the individual channel trends. So not as a standard review thing, but you can shift into a rhythmicity by channel to help isolate certain activity that may be more focal in nature. Let's look at another example of using averages versus individual channel trends. This is looking at a neonatal record, and what we're using on the right are trends looking at FP1 to 01, FP2 to 02, and C3, C4. And we can see the seizures showing up in this trend. But if we're recording a full double distance, there's a argument to be made that you could use, for review, AEEG by channel. And so rather than going across the entire head, we can switch to something that shows us this trend per channel, and things that may be more focal in nature, we may be able to pick out from the trend looking at AEG per individual trend. So that's not to say that average trends are ideal for everything. There are cases where you can have very focal activity, particularly in neonates, where having something by channel can be more useful. Now, we've touched a little bit on asymmetry spectrograms in some of the previous example. Let's dig into what they're actually showing. And we're just looking at an elevation map here to give an idea of using color to indicate red when it's above sea level, blue when it's below sea level. And so the use of red for right and blue for left is just a particular convention. It's one that's used in many places. That can be reverse color palettes are adjustable, but just for the sake of compatibility with colleagues that may be practicing in other places, not a bad idea to stick with this. So in this case, we're using red to indicate higher elevations and blue to indicate lower elevations with respect to sea level. So the sea level right here at the coast, South America, is rendered in white. And so this is showing an asymmetry in amplitudes where we're going above and below sea level. So let's go ahead and apply this to EEG because I think we get the idea. And here we're showing EEG traces below that, and we're showing some trends above that. And this is just something that we'll do when we're showing EEG in relationship to trends as part of this webinar. But as you can see, we begin to squish the EEG vertically, and we begin to compress the trends vertically as we add more trends. And while that's traditionally done back when there were very few trends used, or even with a neonatal EEG when you just had a couple of channels of amplitude integrated EEG and not that many channels of waveforms, it becomes difficult when we start looking at full 1020 recordings and an array of trends. Everything gets kind of squished vertically. And since monitors are larger left to right than they are up and down in most cases, we're going to lay it out like this. So here we've got the EEG on the left, and we got the ability to space everything out vertically so the channels aren't overly compressed, and we can spread the trends out a little bit more too. So this is a standard layout that you'll see in Persyst. Now the artifact reduction is toggled off above the trends and is toggled off above the EEG. That's fairly typical for EEG, but for trends, in most cases, you're going to have that artifact reduction on because, again, you're going to have a larger contribution from physiological artifact showing up in the trend. So let's see what happens when we turn on the artifact reduction. This cleans it up quite a bit over on the right. We see that change in amplitude on the left much more clearly at this point in the trend display. And we see the asymmetry relative spectrogram that's turning blue here pretty much throughout the clinical power spectrum, indicating that we have an asymmetry where the EEG is left weighted at this point. And so if we go a little later in this, we can see where the AEEG is indicating the right has increased in amplitude with respect to the left. And that gives us the context to look at this relative asymmetry spectrogram to say, yes, it's because the amplitude increased on the right rather than the left falling away at that point. So this is just an example to show a different trend layout, one that's traditionally used within Persyst. Again, to space things out, make it a little bit easier to see. So continuing on with looking at our asymmetry spectrogram. And here we're showing it in the context of other trend displays as well. So this is, again, that arrangement where we have trends on the right and EEG on the left, where we can space things out because we're using a full 1020 and we're using multiple trends, and this helps to prevent them from being compressed too much vertically to be able to make good use of them. Now we're looking at a 1 hour trend duration, and let's see what happens when we change the length of that trend duration. We're not really going to be seeing too many cases where we're going to change the range of the asymmetry here, plus or minus 50%. That will typically remain as it is. So you're not going to be adjusting much there, or the frequency range for the adult configuration. Neonatal, it goes down to, we reduce that 0 to 10 hertz because EEG is generally slower. So if we look at the AEG, again, we see this persistent asymmetry where the left is higher in amplitude than the right, and that asymmetry is highest in this theta range. So 1 hour trend duration. Let's see what happens if we go out to a longer trend duration. Now at 24 hours, we can see the asymmetry changing over this extended period of time, and we can see the AEEG showing this gradual increase in asymmetry over this 24-hour period. So for very slowly evolving changes, you can use a longer trend duration to zoom out and see what's happening at that time scale. But there's also a statistical trend that we're going to be looking at versus baseline trend that says, all right, I want to take a look at the EEG with respect to an earlier period without having to go back to that earlier period. I want to have an ongoing comparison of what's happening now versus whether it's minutes, hours, or even days ago. And that can help alert us to changes in the EEG that would be otherwise difficult to see at a 1 hour trend duration. Okay, we looked at FFT spectrograms, and we saw how the horizontal axis was time, vertical axis was frequency, and the color axis, that third axis, was the amplitude at that frequency. So Persyst also has rhythmicity spectrograms, and they're different in that they isolate the rhythmic or periodic components of the EEG and plot those, because when we're seizure hunting, we're often looking for something that is a evolving rhythmic pattern. And if we isolate those rhythmic components at higher resolution than we usually do FFT, then that can be easier to visualize. So let's go ahead and take a look at the anatomy of that. If we take EEG over 90 seconds, here's the onset of the seizure in this first row of channels. We can see it from left to right in this upper third. And if we go down to the middle of this and look left to right, we can see this gradually evolving as it goes from faster to slower. So what if we plotted out the amplitudes by frequency? And this is again what we looked at in the example of the FFT, where we're plotting T3, T5 versus T4, T6. Frequency is left to right, and time is going backwards here. So we're looking at the most recent stuff at the leading edge of this that appears to be closest to us, and then those mountain ranges receding over distance. So let's stretch out the time. So we're looking at 60 seconds. Let's go ahead and change this to 120 seconds. And again, a little bit easier, we can see that something is changing over time. But let's go ahead and make this a little bit more compact. Again, this is the way that spectrograms were rendered back in the day before computers could do high resolution and high color at the same time. But we're no longer in those days. So let's look at a 3D rendering of what this might look like. And so we have frequency here in this axis, 5, 10, 15, 20, 25 hertz. Time is stretching out in this direction. And where the amplitude is highest at those frequencies of the rhythmic components, these mountains get pretty big. So what if we went ahead and color-coded these? So the peaks are the darkest and the valleys are the light color. We get a spectrogram like this. So we have left to right is time. We have 1 hertz at the bottom, 25 hertz at the top. And increasing color, darkness, for this particular color scale indicates increasing amplitude. So what's happening? Well, we can expect that if we compare this to the EEG we were looking at previously, we have a rhythmic pattern that's starting out fast and then going slower because it's going downward. Downward in the frequency scale. That dark color, the darker the color, the higher the amplitude of that rhythmic or periodic activity. Let's go ahead and step through this using our temporary layout, where we just take a subset of trends. We're just taking left and right rhythmicity from 1 to 25 hertz. Time is in our horizontal axis still, but we're showing that one above the other so we can step through it. And let's go ahead and do that. So we're at the leading edge of this. We can see the onset of the seizure. And if we jump to the next point of this, where the trend cursor is sitting at this point where this line has dropped a bit, well, the frequencies have slowed down. The periodic patterns have slowed down. Rhythmic patterns, here we go to the middle of this. It's getting slower still. And as we go successively through this, this is going from faster to slower as we saw in the underlying waveforms. Now let's look at scaling. We talked about the darker the color, the higher the amplitude. But again, spectrograms, and this is something that's commonly missed, is that spectrograms can be scaled just like the EEG. So if you have high amplitude EEG, you might turn that gain down a little bit. Low amplitude EEG, you'll turn it up. Same thing with spectrograms. If they're too faint, you can click on that scale on the right and change the scaling here. So, and what happens? Well, at this scale, as we go from lower amplitude or lower power, and power is amplitude at a particular frequency. That's all it means. So we're going from lower power, lower amplitude to higher amplitude, and it becomes darker through that scaling. So now if we turn this up, we've decreased the gain, reduced that sensitivity, however you want to say it. Now we're at 10. This has become pretty faint. We can't see much in the way of patterns here. And so this is set too high. And if we turn this down to 1, you can see this is off scale throughout much of it. We're already at the darkest color pattern through a lot of the different frequency ranges. So this would be where it's set too low. So if you see something that looks dark like this, just click on that scale legend in the upper right and move that slider to where it's showing you a nice balance of color throughout that frequency range. Not too light, not too dark. You want to be able to see those patterns. Let's look at trend duration. Here's a spike and wave seizure, short, it's about 15 or 16 seconds. And we're looking at a 1-hour trend duration, and this shows up pretty clearly, both of these seizures here. We're at this point where the cursor is placed, and you can see that pattern there. Now with spike and wave, there's not a lot of evolution typically, so you may just see a banded appearance like this. We see a little bit of change as this evolves, but it's pretty static. And short. So this is where using that 1-hour duration for looking at these shorter duration events for seizure hunting is usually much better than doing something like this. Now we're at a 4-hour duration, and these seizures, you can see those patterns there, but they're very thin, just a thin line running through that rhythmicity spectrogram. That'd be tough to pick out from other stuff. So again, duration for seizure hunting, typically 30 minutes to an hour, but if you're looking for slowly evolving changes over time, go ahead and zoom out and get a larger view of that. But don't, the best thing is not to get stuck on a particular duration. Understand that as you zoom out, you're going to be able to see things that are happening over a longer period of time, but you're going to miss those shorter duration changes. Now this last category, we use it for the adult trend panels, not the neonatal. That's a different category. So we're going to talk about this in the context of the standard default trend setup, where you'll have artifact intensity trends across the top of many of the trends. And the types of those are looking at lateral, vertical eye, and muscle, but there's also a signal quality trend that we're going to have a look at as well. So what's happening? Why are we doing this? Well, EEG can certainly have a lot of physiological artifact. Here we have eye blink, muscle going on, and it's contaminated the trends. The trends are showing everything that's happening over on the left, but what we're really interested in is trending that cerebral signal. So let's go ahead and see what happens when we engage the artifact reduction. And so we're showing the original signal on the left in this lighter gray color, and the artifact reduced signal in black. And you can see on the right that the trends become much easier to read. We see the beginning of a alpha showing up on the right. It's linear, it's not evolving, it's bilateral, it's alpha. If we clicked on the trend at that point, that's what we'd see. But the main point is that this trend becomes much less complicated to look at than the previous one. If we go back a page, this has a lot of confounding activity going on. So artifact reduction is usually used for trends to help see that cerebral signal more clearly. And optionally, you can toggle it on and off. There are individual controls at the top where we can toggle artifact reduction as needed on the waveforms. As a matter of tradition, typically you'll use that turned off for waveforms and on for trends. And then if you need to see through some artifact, go ahead and engage it for the waveforms as well. Now, of course, artifact is helpful in an EEG when you're looking at patient state. I can tell that this patient's awake because their eyes are blinking. And if their eyes stop blinking, I don't see those eye blinks in the waveforms. I can tell they probably have their eyes closed. I may see some alpha. It may go into a sleep pattern. Artifact is part of the information that we're recording from the patient, but we don't want it to be in the way all the time. So that's where artifact reduction, being able to engage that for trends, can be really helpful. But I still want to know what's there, and that's this artifact intensity trend at the top. And it's a little small to see here, so we're going to zoom in on that. But the three bands are muscle at the top, and then vertical eye, and then lateral eye. So that gives us a visual indicator of, do we have all these components of artifact present in the underlying EEG, and how that's changing over time, because that can give us a hint about state changes. So let's go ahead and zoom in on that trend. There's the muscle, the vertical eye, and lateral eye. Now, muscle is expressed in microvolts. So as that amplitude increases, this trend line becomes increasingly green. Now, vertical and lateral eye, you can see that these are set, the max is 1. And the reason is there's a neural network that's evaluating the waveforms and saying, what is the probability that this is a vertical eye movement or an eye blink or a lateral eye movement? And it assigns a probability to that, and that establishes the color levels. And let's look at electrode signal quality. So we're reducing muscle, vertical eye, and lateral eye, but when electrodes is dislodged or recording artifact, you can't really recover anything from it. It's not really recording EEG, so what do? It's creating quite a bit of havoc here in the right hemisphere trends. We can't really see what's going on, but it's not all the channels, it's just one. It's the F8 electrode has become dislodged. So the idea of the electrode artifact reduction identifies that as a bad electrode, and you can see it's dashed out here. That's the F8 electrode being dashed out. It's part of two channels in this bipolar derivation. And the trends, well, we recover the right hemisphere trend. So this is without, this is with, and we can see what's happening in the underlying EEG. So an electrode going bad is just something that happens during long-term monitoring. Obviously, you want to correct that as soon as possible, but you don't want to lose the signal between when that electrode goes bad and when it gets addressed. Now, Persyst will indicate that on the electrode signal quality display. During acquisition, you can have that displayed. During review, you typically won't have the electrode signal quality displayed or this numeric display up at the top. You probably just have the comment list open. Or if you're running with an OEM integration, you may fold all these out of the way. There's an X in the upper right. Okay, aside from that, when we're looking at electrode signal quality, it can be helpful to know, well, how long of the recording, how much of the recording had this electrode bad? So if you switch over to the signal quality trend, there's a little drop down at the top, and you can pick signal quality. You can change the duration. This is a case where zooming out might be helpful. And we can see how much over the course of this recording was that F8 electrode bad. And red is increasingly high levels of electrode artifact. And this purple color at the end of the scale indicates that that electrode was marked as being bad by way of an impedance check during the recording. So if that exceeds the threshold that's set in Persyst, it'll go ahead and mark that with a purple color to indicate that it's not looking at the signal from that anymore because it exceeded the disconnect threshold. Maybe that electrode wasn't applied, depending on the application. So easy to read. This is by channel. The redder the color, the higher the level of electrode artifact. Okay, we're going to roll right into part 2 because this part is a bit shorter. It goes more quickly. We're going to bring together a lot of the concepts we looked at and introduce a new trend type. So, and the purpose of that is we want to be able to monitor for changes, whether they're fast, short occurring, or slowly evolving changes, and what can help us with that. One of the new things in Persyst, of course, are these statistical trends or these versus baseline trends where we're going to mark a baseline. The software will mark one initially, or you can place your own as well to say, I want to know what's changing from this point in the EEG by frequency, and we'll look at examples of that. We're going to bring together multiple trends into a single trend panel so we can see how they complement each other, how they paint a picture of what's going on in the underlying waveforms. And then we're going to increase or zoom level out a bit more, showing, well, what if we look at trends for multiple patients in a grid array to see what's happening in a matrix and get an overview of each patient in a live centralized location. Look at web-based monitoring, some notifications, things like that. So we're going to step through the rest of this fairly quickly. So up until now, we've been looking at trends that show what's happening in the EEG for whatever parameters being trended at the particular moment. So if it's deflecting one way or another, or color's changing, it's changing in the underlying EEG with respect to that. So looking for changes is done visually. And if you don't see a change within the trend panel, you can increase the duration or go back to a previous day's recording or go back multiple days. Now, as an alternative, statistical or versus baseline trends allow you to see changes for any trended parameter as a difference from whatever the baseline was set, from wherever that was set. And there's automatic baselines that are set at the beginning of a recording, or you can drop a baseline in to mark a particular patient's state and say, I want to make comparisons from this. In general, though, one question that may have arisen already is this. How do you know when zooming in and out of a trend will yield something useful before you do it? How do you know which recording should be compared with recording stages from hours or days ago before you do it? For some patients, where slowly evolving changes are expected, for instance, delayed cerebral ischemia, recording a parameter at certain patient states and then checking that parameter over time might be done. For example, recording alpha delta ratios for a patient state and then manually comparing them using a statistical measure at periodic intervals every several hours or so. You could do that. And so we can apply statistical measures to EEG. That's not new. One of the shortcomings, though, using statistical measures is EEG epochs are not independent samples. Successive epochs, the ones before that, they're all related to each other, more so than completely independent samples. So that diminishes the utility of using standard statistical measures with EEG. So instead, what Persyst does with our versus baseline trends is we calculate an empirical null and allows for the calculation of normalized Z-scores, even though they're not independent samples from one epoch to the next. So what does this look like? And that previous page of EEG, that's a carotid endarterectomy. We're going to use this for our example of seeing how does this versus baseline trend show differences in the underlying EEG. And what we have here is where the baseline is set. So we click the button above the trends that says baselines. We clicked add baseline, and we added a baseline during a stable section of the spectrogram. So since these are versus baseline FFT spectrogram, left and right hemisphere, it's modeling it based on this. It's creating an empirical null on the spectrogram here by frequency and over time. So what this trend then shows are z-scores either positive or negative, saying what's the difference between this baseline at the beginning and as the trend goes forward. And we can see here, this is where the clamp is. And we can see these negative z-scores accumulating. This is turning darker green, indicating that we're losing z-scores compared to this earlier point. So the difference, again, is important. The spectrogram at the top is showing what's changing in amplitude epoch by epoch. You click here, I expect to see lower amplitudes because I see the shallowing out here, this loss of amplitude indicated by darker colors on the left. Versus baseline is different. I'm comparing it to this point of the spectrogram and it's saying I have less of it here with respect to the earlier state. So it's patient specific, patient dependent. You're marking that, you're saying, I want to know what's changing over time. So what does this look like? Well, if we click at this point, this is where we have this loss of amplitude at the faster frequencies. We can see the right has higher amplitude than the left, and primarily at those faster frequencies. So what does it look like in the spectrogram? There's that darkening color. That's where these negative z-scores show up. Again, this is white, means that is 0. And as it becomes increasingly red on the scale, we're getting towards positive 6 z-scores, increasingly green, negative 6 z-scores, which is quite a bit. And this is turning dark green here, indicating that we've lost predominantly faster frequencies and amplitude with respect to this earlier spot. So what happens if we go a little further? We drop the cursor at this point, and we can see things beginning to turn red here, indicating that we have an increase in slower frequencies, left hemisphere, compared to this original baseline. So that's the important thing to keep in mind, is these are all with respect to the baseline that you've selected, and it happens to be this one that we can see on this page. So let's look at another example. This is a WADA test. And here we're looking at AEG left and right. We can see at the first injection here, amplitude goes up on the right, and that's reflected in the asymmetry spectrograms. This is turning red, indicating that we have higher amplitude on the right with respect to the left at this particular point. Go a little later, we do the next injection, we have an increase in amplitude on the left, the right stays pretty stable, and we can see this increase in asymmetry predominantly at the lower frequencies for the second injection. So how is this versus baseline going to react to that? Because we've marked this baseline here, we're going to model the FFT spectrograms for left and right, and this is what it would look like. So these are all going to be largely green at these injections, or rather red at these injections, sorry. You can see this increasing red patch here, separated out. So we have this increase in lower frequencies fading away, and loss of faster frequencies eventually fades away. And we see the opposite of that for the left hemisphere, this increase in amplitude at both higher and lower frequencies with respect to this earlier baseline. So we'll go to the next, and we'll click at the beginning of this. We can see there's quite a bit of artifact in addition to slowing, but we also have some medication-induced beta showing up on the waveforms as well. So we have this two-banded appearance where this is the baseline, and this is showing the comparison with that baseline. Pretty dramatic example, but this is the idea of illustrating. This will turn red when you have more of it at that particular frequency. Let's go to that next injection. And less artifact here. But again, we have this increase at different frequencies. We have this increase in beta showing up as these final sawtooths showing up on these slower waveforms. So we're seeing the change both in the faster and the slower frequencies with respect to that original baseline. So we've been looking at these trends in isolation to see what are they actually showing, what change in the underlying EEG is happening when we see this change in the trend, what happens when we scale it, time, and gain, and so forth. But we don't look at individual trends because each trend shows a different aspect of the underlying EEG. And so we use multi-trend panels. And this is just an example of the trends that are in the default trend layout, which is the versus baseline comprehensive, because we want to see all these different aspects of the EEG laid out so we can get better sensitivity to different changes, because each trend shows a different aspect of the underlying waveforms. And here we go. This is showing again, a seizure that we've looked at previously. We're looking at seizure probability, spikes greater than 3 per 10 seconds. So we see in this 1 hour trend, we've got 5 seizure detections. Look at rhythmicity spectrogram, we can see these downward sloping patterns, and they're all very similar. So what I would expect is I click on each one of these to review them, that I would see a similar seizure morphology as I go through these, because they have a similar pattern of evolving rhythmic activity. We have our FFT spectrograms, again showing what they've referred to as flames. I think they still do in many places, where you've got the seizure pattern lighting it up in that fashion. We see this asymmetry relative spectrogram, where we have this increase in the amplitude on the right going faster or slower, but we get a little bit more information too. We see that during the interictal pattern, we have the left being more prominent than the right during the interictal period. And what is the reason for that? Did the left increase in amplitude? Well, no. If we go to the AEG, we can see that the left remains fairly stable in amplitude throughout this. The right increases in amplitude during the seizures and then falls in amplitude with respect to the left during the interictal period. We see some changes in heart rate during those seizures, and the versus baseline trends. Because we have a baseline during the interictal period, we can see that dark pattern showing up for each one of those seizures. So we're seeing different aspects of the underlying EEG, but with a multi-trend panel, each one of these works together so that we can increase our ability to see changes in the underlying EEG, even if they're not just evolving rhythmic patterns. And that's not the only thing that we're hunting for when we're using trends. So how can we increase the utility of this even more? Because we can have trends spread across multiple monitors in a central location. But again, now your head is on a swivel trying to see what's happening from one patient to the next. Is there something that we can add to make this a little more efficient? And we touched on this at the beginning of the webinar. What we're looking at here are trends for 6 patients live, and pretty easy to spot in the trends, like, okay, this is something I might want to take a closer look at. I've got seizure detections going on for this patient here. I've got seizures here. You know, the seizure detections and those evolving rhythmic patterns, I can just look up and see, oh, I want to look at this, and this recording and see what's happening. Same thing with this one in the bottom right. And so these are things that can alert you to changes. Now, this is one where we have very slowly evolving changes in the upper left. Again, not everything we're looking for is a seizure. And what these versus baseline trends show us is something that we don't see in the uppermost trends. We see a pretty stable pattern here in all the trends. Not a lot changing from left to right. But when we look at this versus baseline, it's telling me that compared to this earlier period, and in this case it's about 18 hours earlier that baseline was set, I've got an increase in slower frequencies on the left, and I'm losing faster frequencies on the right. So something is changing from when I dropped that original baseline. So here's an example where we can have multiple patients showing. We can see what's happening right now, that these are seizures that are occurring in the present moment. But I can also see the slowly evolving stuff happening from the day before that I might not have been as easily alerted to otherwise. Now, that display of multiple patient trends in a single window, with Persyst Mobile, you can use that on a hospital-based intranet, so using it within the hospital local area network. You could have a display showing the same thing, where we're looking at live trending for each patient. And if we look at the notifications link that's shown here in the browser, we can get live notifications. So this is something where you may have your multiple patient monitor showing those live trends for multiple patients at a central display, and you have maybe another monitor with a centralized display of seizure detections or other notifications from the software, where you can see, have they been acknowledged? There's a checkbox here. We can say, okay, I've seen this. This is not something I haven't looked at yet. And then when you click on one of those notifications, it'll take you directly to the underlying trends of the waveform, so you can see what's happening for that particular patient. So that can be used on an in-hospital browser-based internet, thin client. You don't have to install anything other than a web browser and have authentication to be able to see this. That's set up with IT. But you can also extend the functionality of this through secure methods And there's different ways to do that that can work with the hospital's infrastructure. Doing this with a mobile, either iOS or Android, where you get the same display we're just looking at. You can get notifications on your mobile device, click on the notification, go to the underlying EEG and trends, whether you're in the hospital or outside the hospital, in a secure way. And so we do have some examples that you can log on to and look at those. We're going to actually update this because this is an older link for that. So go ahead and email support@persyst.com, and we can go ahead and send you the latest link for this. So this is the end of our exploration of the different trend types. We do have a separate short screencast on using Persyst Spike Review that can be used primarily in the EMU to group spikes by where they're being where they're detected, and really focus your review and make that a much more efficient process and help increase your yield of recognized spike foci and get a better picture of what's happening in the underlying EEG using that tool. And that's in a separate webcast that we can send you a link to upon request. Really, the intent of this was to go through each trend type and give you a better sense of what that trend is doing. So when I see this pattern, for instance, in the rhythmicity spectrogram, that indicates that I have something that's rhythmic, that's evolving from faster to slower. You can look at that and understand what's happening in the underlying waveforms, click on it, and actually see what's there. Use that to help focus your review and hopefully demystify what's showing up in these other trends as well, but also give you an idea what happens when we use short trend durations of 30 minutes to an hour for seizure hunting, but how that can become more difficult at longer trend durations because we're looking for short duration events. And on the other side of that coin, if we're looking for very slowly evolving changes, how we may want to zoom out in time, but also how that versus baseline trend by tracking changes over time, whether it's minutes, hours, or days, from a baseline that's been set either automatically or manually. You can drop a baseline in and say, I want to see what's changing in those spectrograms versus that original point. So a couple of new tools to be able to help you track changes in the underlying EEG. Always happy to meet by web conference, do some case studies, look at different examples, and answer any questions you have. My name is Michael Guest, VP of Research and Clinical Applications for Persyst. Any questions, please contact me or contact our support team at support@persyst.com, and we'll be happy to connect. Thank you.